So, what we had is a non-exact equation like this mxy dx plus nxy dy equal to 0. So, when you are given this non-exact equation, if you want to make it an exact equation, you multiply it with some mu, okay, some mu function of xy into m dx. Now, mu and dy equal to 0. So, mu is unknown, you do not know a priori. If you multiply some function that makes this as an exact equation, I multiply some mu of xy, so that this equation after multiplying both sides with mu is now the second equation. So, when you multiply mu, this is what it becomes. Now, this is exact, you want this to be exact, such a mu I want. So, what exactly you have seen is it satisfies, mu satisfies some differential equation, some ordinary differential equation, that is then mu satisfied. What you have seen already, that n into mu x minus m into mu y equal to mu into my minus nx. So, then mu satisfies this ordinary differential equation. So, this is actually not ordinary differential equation, this is actually PDE, right. This is a partial differential equation, because you know only ordinary differential, if at all you know the methods to solve ordinary differential equations as of now. So, you want ordinary differential equation, that too whatever you know so far, okay. With these methods can you solve it, okay. So, if you look for mu, if you want mu to be function of x only, if you want that mu to be only function of x, okay, mu as a general thing we have done mu of v, okay. If mu of v, then what you have to check, if it is mu of v, so you just have to check this function my minus nx divided by nvx minus mvy, okay. If v you want x, then you put that x in the place of v and you verify this quantity. If it is function of v only, that means function of x only, then you can go ahead and solve that equation. What you have is d1 by mu d mu by dv equal to whatever you get here as a function of v, okay. If I call this as some function of v, so you have function of v. So, this is a variable separable method, you can solve this equation and you can find mu, okay. So, what is required is, if you are looking for a mu as a function of, as a v can be in specific form, v can be x or y alone, or v can be function of xy like x minus y, x into y, or x by y, or x square plus y square. You can take any complicated form, say sin xy, sin x by y, anything. You can choose whatever may be your y, your v, you choose it as some function of, but is fixed. You fix this v and then verify this quantity, m is known, n is known, v now it is known once you fix it. So, you verify this quantity, and after verifying this should be function of this whatever you have chosen v, some function of v. Then you solve this, you come and put it here and you solve this for mu of xy, v is anyway function of xy, v. So, these are variables, you do not see this is a mu and v, these are the two variables, d mu by mu equal to phi v into dv. So, what is the solution? Mu equal to e power integral phi v dv. This is your integrating factor, okay. So, this is what exactly you have done. So, for if I take x, I will just write at one place for standard forms. What you have to check, if my v equal to x, then what you need to check, my minus nx divided by n has to be phi of x, then mu is e power integral phi x dx functions of x. Okay. If v you take it as y, what you have to verify, my minus nx divided by, put v equal to x, v equal to y, dy by dx. They are two different variables, independent variables. Okay. V of xy you are differentiating, v is only you are taking as only function of y, it is not function of x. Okay. So v is only function of y and you are differentiating with respect to x 0. So this is 0, so you have minus m, vy is 1, so derivative is 1. So this is, if this has to be function of y because phi v is y, so it has to be this, then only then your mu y is, you simply go ahead and write it, so phi y dy. Okay. Otherwise any general v of xy, for example now I write, I will give you list, I list v is this, and then you can go ahead for other forms. Okay. So v equal to, let us say I will just give you x plus y. If you want, if you are looking for in this form, then what you should check is my minus nx, dou m by dou y minus dou n by dou x divided by n into vx is 1 minus m into vy is also 1, dou v by dou y is 1. This should be this, I verify that this should be function of v, that is v is here x plus y, x plus y. Then what is my mu of x y is equal to e power integral phi of x plus y into whatever may be is the variable x plus y. Okay. So this is like d of this, d of x plus y. If it is like this only I can integrate. So this is what is my function of x y integrating factor. Like this you can go on. I will give you one more, v equal to x, if I take x minus y, this will become plus. Okay. Then this will become minus x minus y plus or minus, this plus or minus plus or minus. Okay. So x by y, if you are looking for v as function of x by y, what you have to verify again here. So you have mu my minus nx divided by n into vx is n by y minus minus plus m by mx by y square. Okay. This whole thing should be some function of x by y, then only you can get your integrating factor x y as e power integral phi of x by y d of x by y. Okay. I can easily integrate. Okay. So this is how certain forms, if you are, so but you do not know given equation which form you have to try. So mostly you always check, if it is not exact you check these two, maybe if you have time you can check this, and if it works it is fine. I give you examples where you can use other forms as an exercise. Okay. And I give an assignment, I will give you certain equations where I give you hint that I ask you to choose this v, some form of v, so that you can make the equation exact. Okay. Otherwise we do not know how to exactly how to find such a v so that the non-exact equation becomes exact. Okay. So most standard methods is, this is what you see, v equal to x and v equal to y. So you always verify this one or this one will work. Okay. Most of the textbooks you see these are the things, so, but this is the procedure that works, this is how it works. This is how you make many equations in different forms, many equations you can, many non-exact equations you can convert into an exact equation and then solve it. Solving exact equation, you know the solution procedure, you simply integrate m with respect to x keeping y as it is, and n you integrate from y naught to y and keeping x, fixing x as x naught, okay, equal to constant. That is the general solution, that is straightforward. Okay. So we will move on, we will try to, this is how you, these are the methods you have, standard methods you have to solve general first order ordinary differential equations. Okay. But if you have first order equation as a linear equation, okay, that means you should not have any powers of y or y dash, then it is called linear equation. So, the standard form of linear equation we can write. So, standard form of linear equation. So, linear equation, linear first order ODE. So, so you can put it in the standard form as dy by dx plus some px known quantity function of x into y. So, you can see y dash is here y as it is, you do not have squares or any power of y and y dash, equal to it can be some function of x, some qx, this is what you have, px and qx. This is a standard form of linear first order ordinary differential equation. How do we solve it? Now, you have seen how did you convert exact equation into a non-exact equation into an exact equation. You multiplied some function that is called an integrating factor. So, by multiplying an integrating factor, you reduce that equation into some derivative of something so that you can integrate. So, here also you try to do the same. So, this is a simple first order linear equation. This comes in many practically use whatever you see, many times you come across this equation, linear equations. After simplification of your problem, somewhere you small this, so it is standard to know, you should know how to solve this linear equation and its variant forms. Okay. So, today we will do this linear first order ODE. So, what is the method is as usual, so integrating factor. So, finding an integrating factor. How do you find this integrating factor? Again, so as usual you multiply mu y dash plus px mu y equal to mu q x, mu x q x. Okay. So, this is only function of one variable. So, I can put simply mu x, mu of x. Okay. So, let's I do not know really exactly what is y mu is a function of x or not. So, I simply multiplied some mu. Okay. So, this is equal to, so if I multiply, so the left hand side I expect some form like derivative of, so you see that mu y, so y into mu. If I say, if I write like this, if I can write left hand side like this, then what is this left hand side? Mu times y dash plus y times mu dash. Mu dash means I am doing with respect to d dx, okay, d dx of mu y is this. Okay. So, I want to write this left hand side as this. In that case, you say what I got is mu y dash, that is same, but mu dash y is p into mu into y. So, my mu dash should be equal to px into y, px into mu. Okay. So, mu should satisfy this ordinary differential equation. So, this you know how to solve. What is mu dash? D mu by dx equal to px into mu. So, this I know how to solve, d mu by mu equal to px into dx. I can simply integrate and get the constant. So, that will determine my mu. Okay. So, you have a log mu equal to integral px dx and plus c. Okay. So, this will give me mu equal to e power integral px dx into e power c, that I call it some c1 e power integral px dx. Both are arbitrary constants, c1, c or c1. Okay. So, this is what I got. So, p is a function of x, integral is also function of x, exponential of that. So, it is a mu is a function of x. This is how you get your mu. If you want, after multiplying the left hand side, if you want in this form. Okay. So, now I go and replace my left hand side. So, given equation, I multiply mu with this, if I multiply this by taking C1 equal to 1, if I multiply e power integral px dx into dy by dx plus px into e power integral px dx into y equal to e power integral px dx into qx. I multiply both sides of the equation. So, the left hand side with, if I multiply this with any fixing by c, c1 as 1, this becomes derivative of d dx of mu is e power integral px dx, okay, into y, mu is this and y as it is, equal to e power integral px dx into qx. So, this is known, q is given, this I can calculate because p is given, and I have like this. So, this is like a derivative of something equal to something known, some function of x. I can see if I can integrate both sides. So, how do I integrate this? So, you simply integrate with respect to x both sides, dx dx. So, you get some constant c, okay. C is the integration constant, c is arbitrary. This is your solution. So, this implies e power integral px dx into y equal to c times c plus integral e power integral px dx, which is function of x, qx dx. So, this is your general solution. So, if you bring this exponential the other right hand side, what it becomes is equal to e power minus px dx, sorry, integral px dx, and you have to write it here as well. So, c plus e power minus integral px dx into this, okay. So, this is what is your general solution. This is how you get a general solution of given linear first order ordinary differential equation, okay. So, we will do some examples. So, you will see how it can be done. So, one remark here. See, when I am doing this integration, I did the indefinite integration. So, when I did this integrating factor, I did indefinite integral, simply integral, okay. So, you can also do by fixing some x naught to x, then this c will not be come into picture, okay. So, c will not be there if you do the definite integration, okay. C will not be there, instead c will come as mu value at x naught. So, mu is unknown. So, you are looking for mu, which is an unknown function. If you fix it at some point, some arbitrary point x naught, that will be an arbitrary constant mu at x naught. So, it will come as an arbitrary constant at the end, but you will have integral from x naught to x. X naught you can fix, that should be in your domain. So, if it is nothing is given, you can take x belongs to full R and x naught you can fix it as 0, okay. So, you can take it from wherever in the domain. In the domain you take your x naught and you can integrate. So, sometimes that is useful, sometimes direct indefinite integration is useful, okay. So, as and when whichever is easier we will do in the problems. So, let me give you some example how we solve this, solve these linear equations. You take simple linear equation. So, let us take simple example which is dy by dx plus 2y equal to 1. So, you see that y and y derivative, y dash and y are simple, they are in, they do not have powers, power is only 1. So, okay, the degree is 1. So, this is the linear equation whose solution if you are looking for. So, what is that? P is p of x equal to 2 constant, q of x equal to 1 which is also constant. So, integrating factor is mu of x which is equal to e power integral p is 2 dx, okay. So, you can now, this is always I think good practice to fix your domain. So, x naught to x, okay. So, if you do like this, what is this becomes? So, choose x naught equal to some domain, some point in the domain x naught, any point you can choose. So, because nothing is given, 0 is also part of the domain, x belongs to R, you can choose x naught as 0, to x 2 dx. Okay, so what is this one? This is equal to simply 2x. Okay, so e power 2x is your integrating factor. So you multiply e power 2x both sides of the differential equation. So dy by dx plus 2y e power 2x equal to e power 2x. So this left hand side immediately I can write d dx of mu into, that is e power 2x into y. So you see this e power 2x dy by dx, one derivative. If you differentiate this one, you will get 2y e power 2x. Okay, so this is equal to e power 2x. Now again you integrate both sides from 0 to x. 0 I take it as x is arbitrary, 0 is part of the domain. So you both sides you do it from this. I don't have to write arbitrary constant. Okay, if I integrate both sides from 0 to x, so what do you get? So you will get e power 2x yx, you substitute these limits, equal to e power 2x by 2, substitute this. So this will give me e power 2x yx minus e power 2 0. So that is 1 into y at 0 equal to e power 2x by 2 minus 1 by 2. Okay. So if I take this y naught the other side, this becomes plus y. This is what you get. So what is y? Y is the solution, y naught is an arbitrary constant. Okay. Y is an unknown function. So y at one point, y at 0, because it's unknown function, is arbitrary, it can be anything. Okay. This is your arbitrary constant. So if you say yx equal to my solution y at 0 into e power minus 2x, you bring this e power 2x this side. So this becomes 1 by 2 minus e power minus 2x by 2. This is what you have. So where y at 0 is not known. Okay. When you have like this, so this is your general solution because y naught is an arbitrary constant. If yx is the solution you are looking for in terms of itself at one point, that you can give. So that is still arbitrary. Okay. So you can write this as a constant where c is y at 0, arbitrary, real number. Okay. So this way you can get the general solution of the given linear partial differential equation of first order. Okay. So let me give you now a complicated one, then I close. Then little complicated. So we'll see. So we'll give you. I'll take one more example here. So second, solve. If I ask you to solve this equation 1 plus y square dx minus tan inverse y minus x dy equal to 0. If I ask you to do this, you see by looking at the equation you have a y square, y is tan inverse y. So it is not linear equation. You can expect to solve by other methods. It is not separable method. It is not homogeneous. You see this function is not homogeneous. This function is not homogeneous. So homogeneous you cannot reduce. Reducible to homogeneous it will not work. So exact you try. I don't know. So you may not work. So the best way is assume the domain is not given. So x is, this function is x is defined. So you view this as a y is as an independent variable. So suppose solution is yx. Okay. Suppose this function y is invertible. So I can write invertible function is xy. So in that sense, once you invert this function y of x and you write it as x of y, y becomes independent variable, x becomes dependent variable. So now you view that way, then x is the dependent variable. So you can see that dx is, so you can write dx by dy 1 plus y square minus, so plus x minus tan inverse y equal to 0. So this becomes dx by dy plus x by 1 plus y square equal to tan inverse y by 1 plus y square. So I viewed the equation as though I have a solution that is invertible. So once I have the invertible function x of y, the equation, same equation, which you can view as y as dependent variable, as x as independent variable. Now with this invertible function I can also view as dx by dy equal to something. So that is what is I have. So now x of y is this. So we will solve this equation. So now this is linear. Now this is the linear equation, dx by dy. In the place of x you have y. Okay, the linear equation, how was it earlier? Dy by dx equal to px into y equal to qx. Instead of x you have y now. So this is the linear equation. P is 1 by 1 plus y square. It is not px, it is going to be py here. Instead of x you have y. Qy is tan inverse y by 1 plus y square. So you simply integrate. So what is the integrating factor? Integrating factor mu of, now it is a function of y, e power integral 1 by 1 plus y square dy. So I do not do like earlier here. So this I know, because 1 by 1 plus y square, I do not need to integrate from some fixed number 0, because it is invertible from r to r. Y of x, you can invert it, x to y, y to x, you can go, means that means either x takes all the values and y also takes all the values. You can choose either indefinite integral or definite integral here. 0 to y you can choose, or simply, because you know the integration, I am not doing it. So here this is actually e power tan inverse x, tan inverse y. Okay, this integral value is tan inverse y. So if you multiply this, what you get is d dy of e power tan inverse y into x. What is this one? This is exactly this left hand side. Okay, after multiplying this, if you multiply this integrating factor, so let me write, if you multiply to this, e power tan inverse y into dx by dy plus e power tan inverse y x by 1 plus y square equal to tan inverse y e power tan inverse y divided by 1 plus y square. So the left hand side is simply derivative of d dy. Okay, so d dy of x times e power tan inverse y equal to the same right hand side. Okay, let us call this some function q of y. Okay, so this implies you can integrate with respect to y. So if you integrate both sides with respect to y, what you end up is x times e power tan inverse y equal to integral tan inverse y e power tan inverse y by 1 plus y square dy plus c. C is an arbitrary constant. Okay, so this you can take it as integral tan inverse y, you can take it as t, one variable. So e power t d, if t equal to tan inverse y, dt is dy by, or dt by dy is 1 by 1 plus y square. Y dy, if you bring it to this side, you can write dy as dy by 1 plus y square, this 2 I can write it as dt plus c. This is equal to what you have. So e power t minus e power t, this is the solution. So plus c. So what is t substitute back, you have tan inverse y into e power tan inverse y minus, so e power tan inverse y plus c is my x into e power tan inverse y. You bring it the other side, so this will give me x is now dependent variable, it is a function of y, x of y equal to tan inverse y into e power tan inverse y, and if you bring it the other side, e power minus tan inverse y, that goes minus 1 Okay. So, this whole thing into e power tan minus tan inverse y is thus plus c times e power minus tan inverse y. So, this is your general solution. Okay. You view assuming that you have an invert you have a function y of x that is invertible. So, that means you can write as x of y. You change the independent variable into dependent variable. That is possible only if you can go from x to y and y to x. It is invertible map. Okay. So, you have something like this. So, if you have e power x or simply some curve which is defined for all values of x. For all values of x is defined, this is x, this is y. So, you can also view this as like this, x as a function of y. So, it is invertible map. Okay. So I hope you know. Then once you have this, so you can easily see whether you have you can invert this. Okay. So, this is the general solution. So, this is the general solution of the given equation. Okay. So, you can simplify if you really want as y, you want to view y as a function of x, you can do that. How do we do? You invert this this implicit relation. Okay. So, inversion you can also get y of x, y in terms of x. Okay. So this is how you can solve a linear first order ordinary differential equations. So, I have given 2 examples. We can also do some more like this. Next we will do some equations which are not exactly linear equations, but they are close to the linear equations that can be made them linear equations by some way. Okay. So, we can reduce them into linear equations and then follow the same procedure which you have done for the linear equations to find the general solution. Okay.